Hello everyone, welcome back to my channel. My name is Dr. Yogita Bish and this is the fifth video of my video series Chemical Bonding. So till now I have discussed everything about the Lewis approach. We started with the basic postulates and what this approach all about, that is the octet rule, how to represent that, and then we also studied how to calculate the formal charges, lone pair electron, bond pair electron, total valence electron. That is very important to understand the step by step procedure to show the Lewis structure of any molecule. And this formal charges is also very important to guess or to determine which structure would be preferred as per the Lewis structure or the Lewis approach. Okay, so if you haven't watched those video, I would highly recommend you to watch those video to understand this concept properly. Then in last video, today's video, this will be the last video for this Lewis approach. In today's video, we will talk about the limitation of the octet rule, and the next video onwards we will move to the other modern approaches which explain the chemical bonding, that is why certain molecule combine together in a certain fashion, and what are the criteria for discussing their for their particular shape and their stability. All those would be discussed in the next videos. Okay, so let's just begin with the limitation. So the first limitation, which many books doesn't actually consider as a limitation, because of the obvious reason that in case of hydrogen and oxygen, they both follow the duplet rule rather than the octet rule. Whereas the Lewis dot structure, its basis is the octet rule. According to the octet rule, it says that every atom try to have 8 electron in its valence shell. Okay, whereas in case of hydrogen and helium, it is not possible. The maximum number of electron they can have in their valence shell is 2. That's why rather than following the octet rule, they follow the duplet rule. Okay, let me just show you. The configuration for hydrogen is 1s1, right? So it requires only 1 electron to complete its valence shell. That is why it form, like in case of water, it form structure like this, right? Because it requires only 1 electron, it can take or share this with the other oxygen atom, and its octet, or others, I would say the valence shell will be complete. Right, same goes for this hydrogen. What about this oxygen? This oxygen, it is going to take one or the share 1 electron for this hydrogen and another for other hydrogen. So it will complete its octet, that is, it will have the 8 electron in its valence shell, whereas these hydrogen, they will have duplet in their outer shell. Okay, same goes for the helium. It also doesn't follow the octet rule. Why? Because it has 2 electron in its valence shell rather than 8 electron. Okay, then the second limitation is the incomplete octet of lithium, boron and beryllium. Okay, for that we need to understand the configuration again. So lithium has a configuration of 1s2 2s1. Beryllium has a configuration of 1s2 2s2, and boron has a configuration of 1s2 2s2 2p1. Okay, so 1s is of no use in this particular case. Why? Because Lewis structure is based on the valence shell. Valence shell electron means the electron which are present in the highest principal shell. Okay, so in this case it is 2. So we will be considering only electron which are there in the principal quantum number 2, right? So in this case the valence shell electrons are 1, in this case it is 2, and in this particular case it is 3. So how many electron does it need to complete its octet? It has only 1 electron in its valence shell, so it requires 7 electron to complete its octet for octet, right? This require how many? 2 electron it has in its valence shell, so it requires 6 electron. Whereas boron, it has 3 electron in its outermost shell, 2 plus 1 3, so it requires 5 electron for the octet. Now you can see that all these atoms, they require high number of electrons, 765. So they find it easier to give up the electron they have. For example, lithium happily give up 1 electron rather than gaining 7 electron to complete its octet. Similarly for beryllium, and same goes for the boron. They prefer to lose electron rather than accept more electron to complete their octet. So in that case, what will happen? When lithium is going to lose 1 electron, its outermost shell electron will have 2 electron, right? This also have a 2 electron, this will also have 2 electron. They are not left with the octet, rather than they will left with the duplet. Okay, that is why this is also the violation of the octet rule. Okay, for example, I'll give you example of a boron chloride. So here it formed something like this. Okay, so chlorine has 7 electron, so we can show it like this. Please do follow the stepwise representation of the Lewis structure. I'm not going into the detail because I have already explained that in the previous video. So in this case, each chlorine has 7 electron and it requires only 1 electron. So it is going to take it from the boron. So its octet is complete, and this chlorine also has a complete octet. What about the boron? If it try to gain 1 electron from these chlorine and it already had 3, then also it will left with only 6 electron. That will be the incomplete octet, right? So it will not complete its octet. Even if it is giving up the electron, then also it is not and it will not end up with the octet. Okay, so in these 3 atoms, these are the exception. They never end up with the octet. Okay. Then the third limitation is odd electron molecule. There are many a time you will encounter that certain molecule, they will have odd number of electron. So there is no point, at any point they are completing their octet. The famous example is nitrogen monoxide. Okay, so if I try to draw the structure for this, it will be a good recap for you also, like for how to draw the step-by-step structure of the nitrogen monoxide. For that, first we need to find out the total valence electron. So in this case, total valence electron, it is the sum total of the valence electron of nitrogen and oxygen. Nitrogen has 5 valence electron, oxygen has 6, so total 11, right? And then we have to find out there are only 2 atoms, so there is no point of guessing the central atom. This is how they look. So the lone pair electron in this case would be total valence electron minus bond pair electron. So total valence electrons are 1 minus bond pair electron, whatever the single bonds are there, multiplied by 2, only 1 are there. So 1 into 2, 2. So lone pair electrons are 9. So we have to arrange these 9 electrons around these atoms. Okay, so let's just do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9 nitrogen end up with 1 single electron. You can show it on oxygen also, but as per the formal charges, that is not possible. So this is one structure which is possible in case of nitrogen monoxide. So if I don't know whether it is a correct structure or not, let's just check, right? So for that we need to find out the formal charges. Okay, so in case of oxygen, the formal charges would be, I hope you do remember the formula for the formal charges, that is the valence electron minus lone pair of electron, in this case it is 6, minus bond pair electron. How many bond pair electrons are there? 2 divided by 2. Okay, this was the formula. If you don't remember it, please go through the previous video. You will recall, you can easily recall that. Similarly for nitrogen, the valence electrons in case of nitrogen is 5, minus how many lone pairs are there? 3, minus bond pairs are 2, 2 divided by 2. So in this case it will be plus 1. So this nitrogen has minus 1 charge, this oxygen has a minus 1 charge, this nitrogen has plus 1 charge. Okay, so now As per this stability that we discussed in the case of formal charges, it was suggested that if it is possible to reduce these charges somehow, then that structure would be considered more stable, right? So what we can do it, rather than having 6 lone pair of electron, let's just use these 2 lone pair of electron to form a double bond. Okay, so the other structure which is possible in this case would be oxygen double bond 1 2 3 4. Okay, and we are not going to touch the lone pair on nitrogen. Again, let's just calculate the formal charges in this case. So in this case, oxygen, what will be the formal charge on oxygen? It will be oxygen, and the valence electron in oxygen is 6, minus lone pairs are 1 2 3 4, minus bond pair are 2 plus 2 4 divided by 2, so it will be 0. Okay, in case of nitrogen it will be 5 minus lone pairs are 3 minus bond pairs are 4 divided by 2, it will be 0. So in case of second structure, the formal charges on both nitrogen and oxygen are 0 0. So as per the formal charges, second would be preferred as compared to first. But in both the cases, you can easily see that only 1 electrons are there on nitrogen. Okay, so is it leading to the completion of the octet in case of nitrogen? In case of oxygen, yes, both the structures 1 2 3 4 5 6 7 8, but in case of nitrogen it is 1 2 3 4 5 6 7. In the first structure also it is 7, but they do have a stable structure. It is possible to for this particular molecule to exist, right? So that is another violation of the octet rule, where nitrogen monoxide has this structure, but the octet of nitrogen is not complete, rather it has the odd electron. Okay, then the most important limitation I would say is the expanded octet in element having d orbital. So if you go through the periods which is 3 or more than 3, you will realize that they have the d orbitals. Okay, so that is why they show more than whatever the valency we are expected from the other member of the previous period, like for example second period. In case of nitrogen and phosphorus, nitrogen present in the second period, phosphorus present in the third period. But in case of nitrogen we don't have the d orbital, whereas in phosphorus we have the d orbital. That is why phosphorus show different covalency as compared to that of nitrogen. I have already discussed in detail in the previous videos. So because of this, what happen is, rather than completing an octet, it has more than 8 electron. It is possible to have that. Okay, let me just show you with the help of example. The phosphorus has a configuration of 1s2, 2s2, 2p6, 3s2, 3p3, and of course it also have 3d orbital. Just for the sake of representation I am showing it. There are no electron. This is 3d 0. Okay, I don't even need to show it, just for the explanation I am showing it here. So I am not interested in the inner shell electron. These are of no use in case of Lewis structure. We are more interested in the valence electron. So in valence electron we have something like this. If I have to represent this, I can represent it like this. This is 3s, 3p, 3d. Okay, 1 2, and here we have 1 2 3, and d is empty. Okay, but since d is there, d orbital is there, and it also have the same principal quantum number, so their energies is comparable. It's not same but comparable. So it is possible to move one electron to this side to have something like this. One electron here, one electron in each p, and also one electron in d orbital. Right? So how many electrons, unpaired electrons are there? 1 2 3 4 5. Okay, that is why it is possible for phosphorus to show a covalency of 5, which was not possible in case of nitrogen. Why? Because it didn't have the d orbital. So the only covalency the common covalency it can show is 3. Okay, so this is how it look like. So we are not talking about again the shape, just the structure. So fluorine require 1 electron, so it can take 1 electron from phosphorus. At the same time, if we calculate the octet of phosphorus, how many electrons are there in the outermost shell of phosphorus? 1 2 3 4 5 6 7 8 9 10. 10 electrons, whereas the octet means 8 electron, but it is a violation, right? So it is having more than 8 electron. Okay, but this is absolutely fine structure as per the Lewis explanation. As per the structure or explanation, it says that the central atom can have more than 8 electrons. So that is also another I would say the limitation of the Lewis approach, that it says that the central atom is allowed to have more than 8 electron. Same goes for the SF₆ also. As sulfur also has the d orbital, wherever d orbital is there, it is possible to show more than normal covalency, and that is why it is possible to have more than 8 electron in the valence shell. Okay. Then the fifth limitation is the formation of the compound by noble gases like xenon fluoride, krypton fluoride, etc. So as per the Lewis, the ultimate goal of any atom is to have 8 electron in its outermost shell, and once it has a complete octet, then it should stop at that point. That means it should become inert, it should not react with any other atom, it should not combine with that any other atom to form a molecule. But that is definitely not happening in these noble gases. So he was unable to explain this behavior as well, that despite having a complete octet, they are still forming the bond. So that was another limitation. Then I have already said this multiple times, that it do not talk about the shape of the molecule, it just talk about the structure. But why certain molecule have a tilted structure, that is the lone pair repulsion and all those things, based on that certain molecule has a linear structure, other has a tetrahedral structure. So those shapes are not being explained in this particular approach. Okay, for that we need another approach for the explanation. Okay, at the same time, it doesn't give the explanation for the stability, energy, bond length, bond polarity. There are so many concepts this particular approach was unable to explain properly, and it also doesn't explain the magnetic properties of different molecule, and also, which I have not written here, it also unable to explain the incomplete octet, or the approach is failed to explain the molecule formed by the transition metal atom. They sometimes show variable valency, sometimes in certain cases they show other valency, other cases they show other valency. It was unable to explain that concept as well. Okay, so all in so to summarize, we can say that yes, Lewis structure or the Lewis approach was very good approach, because it was easiest to understand, and it gives the basis of any molecule, like why they form the bond, why they come closer. But there are still many questions they were unable to answer just based on this approach. Okay, to answer those questions, we have to understand the other approaches as well. Okay, so in the next class onwards, we will start learning those approaches. Okay, so if you have any doubt regarding the Lewis structure and these exceptions or formal charges, anything related to the octet rule or the Lewis approach, you can just comment below, and I'll try to justify or give the answer for those questions. Okay, so I'll see you in the next video.